Hello everybody. A very warm welcome to our new webinar series, In-Depth Application Knowledge from Experts. My name is Elizabeth Ebner. I am Marketing Manager at Xanh, and it's a real pleasure for me to guide you to our webinar today. I am extremely happy to see many of you joining today from all over the world. So this is also a good evening to our Asian friends, a hello to our European listeners, and a good morning to our US audience. Many of you already know Xanh. Xanh is a leading provider of online water quality monitoring systems with more than 20 years experience, and since the year 2020, we are also proud part of Badger-Meter Inc. And we have now prepared an exciting webinar series for you, where our Xanh experts will talk about different water quality monitoring applications. And I'm very excited that today we will talk about wastewater. Typical applications of Xanh products in municipal wastewater will be shown. So we will go from pollution load monitoring in sewer systems to compliance monitoring in final effluent. This presentation will also include well-selected case studies and also hand-picked wastewater parameters. Today's presenter is Franz Hofstetter, which you also see on the video. He has a background in mechanical engineering, in civil engineering, and water management, with a Master of Science at the University of Natural Resources and Life Sciences in Vienna. He joined Xanh as Head of Customer Services in March 2021, but he was already part of Xanh from 2000 to 2012. Initially, he was developing applications and spectral algorithms for the spectralizer, and he was also working for Xanh as a sales director. So this will be the first part of our webinar series, but in November, you will get a chance to hear about our drinking water applications, and in December, we will also share our knowledge about environmental monitoring, both also well worth spending some time with. At the end of each session, you will also have the chance to ask questions that might occur during the webinar. We have a few guidelines for our webinars. One of them is your microphone is muted. So we have done so to reduce the background noise, and with this to allow the best sound experience possible for all participants. In case you have any questions during the webinar, we are extremely happy to answer them. So please use the questions function, which you can see on the right-hand side. And we will then collect all the questions to avoid the confused talking during the webinar. In the end, the answers will be answered during our question and answer session. In case that we're running out of time, all of the collected questions will be answered in written form, and we will put it on our customer portal for you to read afterwards. And last but not least, very often asked and asked for, this webinar is recorded. So the video will available be afterwards on our website. And having said all that, I'm very happy to hand now over to Franz. Franz, the stage is all yours.
Thanks, Elizabeth. Thanks all for joining this webinar. My name is Franz, and as announced by Elizabeth, we will talk about wastewater applications now. We won't be able to focus to each and every detail of wastewater applications, but we will give you a good overview about wastewater applications. To get a real full picture, you will have to join also other webinars and trainings offered by us. At first, a short story about the path of the water, how the water circulates in water industry. The drinking water utility, you can see it on the top, produces drinking water. This drinking water is supplied to households as well as to industry. The drinking water is following the light blue arrows. The households and the industry, they consume the drinking water and turn it to wastewater. This is the orange arrows, and this is the part we will have a look today. After the wastewater treatment plant treated the wastewater, it's released to natural waters, and these natural waters are used again by the drinking water plants. Here we can see a wastewater treatment plant. We from S can divide the wastewater applications in 4 typical applications. The first is the sewer system. The second is the influent of the wastewater treatment plant. The third is the biological treatment of the wastewater. And the fourth application is the final effluent of the wastewater. Here you can see the wastewater treatment plant a bit more in detail. In the beginning, the raw sewage is cleaned by the screen and the solids are settling in the primary clarifier. These 2 applications we call sewer and influent application, and typically following parameters are monitored in these applications: organics, either CUD or BUD or UV254, suspended solids, TSS, hydrogen sulfide, and ammonium. The next stage is the biological treatment. In the aeration basins, the ammonium is converted into nitrate, and the CUD, the organics, is consumed. Typical parameters monitored here are the total solids, the nitrate, sometimes the nitrate, the ammonium, of course the dissolved oxygen, and the pH. After the biological treatment, the second clarifier and sometimes also an advanced treatment, the so-called 4th stage treatment, takes place before the wastewater is released to the rivers. Typical parameters monitored here are solids or turbidity, organics again, nitrate, ammonia, all the species of nitrogen, pH, conductivity, and if there is a disinfection, also ozone and free and total chlorine are commonly monitored here. In the sewer systems, we have following applications. We do pollution load monitoring, compliance monitoring driven by government, combined sewer overflow monitoring. This is highlighted blue because we will have a detailed look to this today. We try to detect untypical discharges, contamination. It goes up to identifying industrial discharges that are polluting the wastewater. And last but not least, prevention of corrosion damage and smelling control. In the wastewater plant, the first station is the influent. We are monitoring here again the pollution load. We try to protect the plant from too much water or toxic events, especially the biological treatment can be endangered by toxic substances. The process control of the sedimentation or the coagulation taking place in the first clarifier can be process controlled, and buffer tanks can be managed on this location. Now the water goes to the biological wastewater treatment, and what we are doing here is we are controlling the process of the aeration, the nitrification, the denitrification, and we are monitoring the sludge concentration. In the effluent, the water is already cleaned. Compliance monitoring is a big point here. Government forces the wastewater treatment plants to monitor their effluent. The process control of sedimentation taking place in the final clarifier, controlling the forced treatment stage if present, the ammonium control of the biological treatment, and of course the efficiency of the complete biological wastewater treatment. Now we go directly to applications, and we start with the sewer systems, point 1 in this slide. Before doing so, I want to highlight the most important parameter in the wastewater world, and this is the chemical oxygen demand. The chemical oxygen demand is no concentration of organics, but rather it's the oxygen that is consumed by those organic substances per volume of water. The method is oxidizing chemically all organic and also some inorganic compounds of a water sample, and it's broadly used as a non-specific indicator for the pollution of wastewater with organics. The COD can both result from natural sources or from human sources, and it consists both of dissolved and particulate matter. The COD is monitored in wastewaters and also in environmental applications to ensure the regulations of government are met, to control the biological treatment processes of the wastewater, of course to protect natural waters, but also the intake of wastewater treatment plants, to monitor the COD load resulting from industrial effluents, and each and every wastewater treatment plant monitors the COD, so it's really broadly used worldwide. The laboratory analyzes the COD taking samples of water. The carbon is oxidized chemically, and the oxidant that is not consumed is measured. Some inorganics, e.g. chloride, can falsify the results, and many laboratories are using not the standard lab method, but rather quick tests instead. Absorbance measurement are well proven to monitor COD worldwide. Many substances that are consuming oxygen are also absorbing UV radiation. That's why we can monitor it with our instrumentation. The ice can, the spectrolyzer, they monitor the COD by means of many wavelengths absorbance in the UV range and in the visible range. It is pre-calibrated X works and is equivalent to laboratory. There are a few reasons to calibrate the COD of the ice can and the spectrolyzers. Aging is not a reason to calibrate it on a periodical basis. The reasons are to initially adapt to the local water matrix. This is done one time during installation to meet the results of the local lab and to comply to regulations. Here you can see how we monitor the COD. I won't go to the details now, but the most important sentence is highlighted in bold letters. The higher the concentration of the substance causing this absorbance, the higher is the reading. That means the concentration causing the absorbance can be monitored by absorbance measurement. Now back to the sewer systems. What are the measurement goals and what is the purpose to monitor in sewer system? Pollution load monitoring, compliance monitoring, industrial discharges monitoring, detection of untypical discharges and contaminations, combined sewer flow monitoring, smelling control and corrosion damage prevention, and managing sewer retention and buffer basins. What are the special challenges here? The special challenges when monitoring in this application is the risk of clogging and fouling, e.g. fat can cause window fouling, the risk of damage due to foreign matter and extreme flow conditions. We will come to this. Lack of infrastructure and excess, risk of explosive atmosphere, and laboratory samples being not representative. The S-can solution for this application is either a submerged installation or a bypass installation. You can see the pictures on the right-hand side. The spectrolyzer is very robust in design and can withstand harshest conditions in the sewer. Auto cleaning is typically done via compressed air. Sorry, I was too fast now. Victoria, may I ask you to take over and now it's here.
Of course.
Can you go back one slide? Another slide back, please. Thank you. So the auto cleaning is typically performed with compressed air. The monitoring stations of S can have a small footprint and can also be controlled remotely, which is a big favor in sewer applications. What are the benefits for the customers? They quantify pollution loads. Sometimes this is even used for accounting. They're reducing the overloads of wastewater treatment. They can identify industrial discharges and polluters. They can avoid toxic events to reach the plant's microbiology. They can preserve evidence of events by controlling autosamplers. They can reduce the pollution loads discharged to natural waters, reduce damages from corrosion, and reduce smelling. Here you can see the product's configuration we use typically. We use the spectrolyzer industrial, sometimes a non-standard ponton or open tanks. You could see the pictures on the last slide. The S-can compressor for automatic cleaning, the Concube with its multiple data transfer options, Monitool software, which can calculate loads using the free formula. That means we can simply integrate flow meters from our new sister companies and calculate the load by multiplying CUD with the flow. And we can also trigger autosampler using the Monitool software. Anatool, the special software, is used for detection of industrial discharges. Here we can see now an overflow event in a combined sewer system. And you will see, now you can see how the water flow increases over time. The swimming boat carries the spectrolyzer, and the flow is getting worse and worse, and like a surfboard, the instrument is still running and monitoring. Now you cannot see it anymore, but it's still there and giving results. Now the rainfall stopped and thus the flow is reduced, and finally the instrument is in well condition and did provide results all the time. This is the first case study we present today, monitoring of combined sewer overflows. The measurement goal and purpose in this application is to reduce the pollution load, both the pollution load discharged to natural waters and to manage at least the pollution load treated by the wastewater treatment plant. Special challenges when monitoring this application is the risk of clogging and fouling, e.g. fat, the risk of damage due to stormwater conditions, you could see them in the video, and the risk of explosive atmosphere. S-can solution were floating installation, customized, and spectralizer industrial. This is specified to be explosion proof and can work up to 10 bar pressure. Here you can see some pictures from the movie you've seen before. The benefits for this customer were to monitor the pollution loads discharged both to natural waters and to the wastewater treatment plant. They developed a new sampling procedure for sewer systems. They called it 24-hour sampling campaigns, and they published dozens of scientific publications worldwide. The parameters monitored were chemical oxygen demand and solids. Here you can see some parameter results. Over 2 days, and the configuration they used was spectralizer industrial, the global calibration influent. They did also an advanced local calibration. Our colleagues did support them, and in this way we were able to match the laboratory very, very precisely. The S-can pontoon, a customized solution for installation, was used. S-can compressor for automatic cleaning was used, and the constat was used. This was the older model of the cone cube nowadays. So the next application we take a more detailed look is the biological wastewater treatment plant, the point 3 in this sketch. What is the measurement goal and purpose in this application? The most important goal in this application is to reduce the operational costs. The blowers producing the air are by far the most important cost factor because they consume a lot of energy. Therefore, the process control of the aeration is very important. Of course, the control of the nitrification and the denitrification and the monitoring of the sludge concentrations are important as well. Special challenges when monitoring this application is that the processes of the microbiology are very fast, and therefore it's required to monitor in situ. The sensors have to be proper positioned in the basins to be able to catch really representative water qualities. Different processes can take place in one basin. Laboratory results are often falsified by processes ongoing after sampling. The laboratory samples are often not representative, and there is a certain risk of fouling due to the coagulants, bacteria, and algae, and the solids concentration being already pretty low. Here you can see Our solution is a submerged installation. There is no use to pump the water out of the biological treatment reactor. This will be completely wrong and lead to false results. And the compressor for automatic cleaning, you can see in the picture to the right that the cleaning works efficient. What are the benefits for the customer? Minimizing the organics and the nitrogen discharged to the natural waters, reducing the air and oxygen to be produced. Energy consumption is a big point here. Reducing the costs for treatment plants operation is the main driver for this. Typical products we use in this application is the nitrolyzer to monitor nitrate and solids, the ammolyzer to monitor ammonia, the solubilizer for solids, the oxylyzer for oxygen. And for submerged installation, we use the carriers. For automatic cleaning, we use S-can compressor. And as a terminal, both the conlet and the con cube are used. Here you can see some results. Red, you can see the oxygen. Blue, you can see the ammonia monitored by the ammolyzer, the oxygen monitored by the oxylyzer, and you can see the aeration cycles driving the nitrification. A case study in this respect is a wastewater utility in Colorado Springs. As you can see here, the operators are pretty happy with our solution, and they even mentioned that they were able to lower the daily operational costs by means of our products. What are the goals in this case study? To process control nitrification and denitrification and the aeration blowers. Special challenges when monitoring these applications was the distance in between the sensors and terminals. So there was based on the design of the plant, there was a big distance in between the terminals and the sensors, and we had to overcome this. Our solution here was nitrolyzer and ammolyzer and oxylyzer being submerged to the aeration tanks. The data transmission was done via radios to the concube. This was a customized solution. The auto cleaning, as typical in this application, via compressed air. The benefits for the customer were to optimize the nitrate elimination by the bugs, low maintenance efforts and easy installation, and they reduced the operating costs significantly. The parameters monitored here were nitrate, solids, ammonium, pH, and dissolved oxygen. In the graphics, you can see green the ammonia and red the nitrate. Dissolved oxygen is blue, and you can clearly see the periods of aeration and the nitrification following exactly the periods of this aeration. Ammolyzer, oxylyzer, nitrolyzer, and concube were used in this case study. Again, you can see here the wastewater treatment plant. Now we go to the last application, the municipal wastewater effluent. What is the measurement goal and the purpose in this application? Compliance monitoring. A lot of governments force the wastewater treatment plants to monitor the quality of the final effluent. The monitoring of the biological wastewater treatment plant's efficiency, process control of the sedimentation in the final clarifier, process control of the forced treatment stage, and ammonium control of biological treatment. Special challenges when monitoring this application is fouling due to coagulants, algae, bacteria, and the absence of solids. S-can solution for this application is either a submerged application or a bypass installation. So both options are possible. Auto cleaning can be done via the compressor or with the auto brush. You can see here as an example the rucksack, which is a submersible auto brush that is clamped on the spectrometer, and periodically brushes are removing fouling from the windows. On the right picture above, you can see that the windows are kept clean by these automatic brushes. What are the benefits for the customers? Minimize the solids discharge to the rivers, preserving the evidence of compliance, optimizing biological treatment, and reducing costs for treatment plants operation. Typical S-can products configured and used in these applications are the spectrolyzer, the nitrolyzer, the carbolyzer, the iScan, the optical probes for monitoring nitrate, COD, TUC, solids, etc. Ammolyzer for ammonia, condolyzer for conductivity, solulyzer for solids. We use either S-can carriers for submerged installation or S-can microstation for bypass installation. On the upper picture, you can see a submerged installation. The S-can measuring devices are submerged directly in the effluent channel. On the lower picture, you can see a microstation. This is how we produce stations for wastewater final effluent in bypass. Also, the compressor can be seen on these pictures on the right-hand side. We use either the compressor or an auto brush, the con cube or the con lattice terminal. We also prepared a case study for this application, and this is ammonium discharged to waters. The challenge and the goal in this application is its compliance monitoring driven by the government. The special challenge is to precisely monitor in between 0.1 and 5 ppm ammonia. Therefore, lowest cross sensitivities are needed, and special challenge in this application was that the government is looking to this very carefully. In the graphics, you can see the perfect correlation from laboratory results to the ammolyzer's results in the range from 0 to 5 milligrams per liter, and a lot of samples are below 1 milligram per liter and also correlating perfectly. S-can solution was an ammolyzer, including compensation for pH and including compensation for potassium. So we need the ammolyzer to be compensated for possible interferences in this application. Auto cleaning was performed via compressed air. Benefits for the customers was that the nitrification was improved and the ammonia discharge to the river was reduced significantly. Here you can see results over weeks or even months monitored at this station. The ammonia is monitored red, and you can see often the ammonia level is below 1, but sometimes there are events that are 5, 7, 10 milligrams up to 10 milligrams. The products we used here was the ammolyzer, the S-can carrier for submerged installation, and the terminal con light for operations. So now I'm through with the wastewater applications, and it's time for questions and answers from your side. I guess Elizabeth has collected some already.
Yes. Yes, first of all, thank you, Franz. Let me thank you for this very interesting presentation and showing us such a broad range of different applications in wastewater. In the meantime, we have collected a few questions, and I would say let's get started right away with that one. Franz, which application is the most important one in wastewater, in your opinion?
In my point of view, the most important one is for sure the biological treatment. The first reason is it's commercially the most important, because operating the blowers consumes so much energy, and reducing the amount of oxygen needed, or the optimizing the process control of the blowers is by far the best method to reduce the operational costs. And there are studies that saying that up to 70% of energy can be saved if the aeration tank is controlled carefully. And furthermore, the nitrogen removal in the biological treatment has to be monitored in situ. It makes no sense to take a lab sample, not only due to time, but you have to be really inside the reactor to know what is going on. You cannot even pump the water out of the basin and put it to a bypass, to a measuring station operating the bypass. This makes by far no sense. So these 2 points are for me the reasons why the biological treatment plant is by far the most important one. I can imagine some would say monitoring the final effluent is more important, because we have to protect the natural waters. But frankly spoken, in this application, you can do a lab sample 2 times a day, and you will be able to monitor the water. Whilst in biological treatment, this is fully impossible. You have to be monitor in situ, and you have to monitor really online the water quality. There's no question not to do it that way.
Mm-hmm. Interesting. So would you also say that this is the most the application that we as S can do the most in wastewater?
On quantities, I would say so, because typically wastewater treatment plants, they don't have only one basin to perform the biological treatment, but they have several basins, and each basin typically has to be process controlled, has their own aerators, and so you need multiple devices for multiple basins.
Mm-hmm.
So yes, on quantity, great. I would say this is most often in wastewater done by SCAN.
Thank you. Good. Let's move on to the next question. And in the meantime, I'd like to say, in case someone else still has questions, please feel free to put them in the question box. We're still collecting them, so if you feel like the questions, or even if it pops up afterwards, we're happy to answer them. So let's move on to the next one. Why don't you use automized brush in other application than effluent?
Good question. Somebody watched carefully. There are in wastewater influent, we typically use compressed air for auto cleaning. The performance of the compressed air auto cleaning is very good in the influent, and also further down, as long as there are particles present. These particles, they support the automatic cleaning via compressed air. There is a kind of sandblasting effect which helps to keep the windows clean. So this is due to performance, we use the compressed air cleaning in influent and in aeration tanks. Whilst in the final effluent, it might be that there are, or it should be that there are absolutely no solids are present, and therefore the automatic brushes are sometimes the better solution. And there is also an operational issue if you cannot operate an rotating brush and moving part in the influent. We have here hairs and toilet papers and all those stuff, and they would clog the not only the instrument but also the brush, and the motor won't be able to rotate the brush, and it would simply not work. It would simply be damaged because it would be wrapped, and the compressed air cleaning, it blows simply away all the stuff, and there is no risk of clogging or of wrapping the device.
I see. And I think this also somehow almost answers another question which I can see here. It says, is it possible to use in combination air compressor and auto brush cleaning?
Actually, technically, we would be able to manage it in some way, but so far I know no application that would need this combination.
Okay.
So it makes absolutely no sense, and it would be too complicated configuration. But technically, it might be possible. Yeah, I'm sure.
Fair enough.
When you force us and send us a lot of questions, my colleagues and I from support team, we would find a way to do it. But it's not it's not foreseen. Let's call it that way.
Fair enough. Thank you. Let's move on to another one. In a wastewater treatment plant, suppose we are monitoring influent as well as effluent. Can both installations be controlled, monitored by a single concube?
This is possible indeed. We can connect many sensors and to one terminal concube, and could control the readings and display the readings on one concube centrally. Of course, in respect to power supply and automatic cleaning, we have to establish infrastructure both in the influent and in the effluent, but the controller can be located centrally, and we can even use it to display the difference of the water qualities in the final effluent and in the influent. So you could even see how the wastewater treatment plants performs. You can see the cleaning effect because you can see the parameter readings in the final effluent and the parameter readings in the influent on one screen. Of course, there will be a time delay. The process of treatment takes some time, but yes, this is possible, and even a good application for SCAN, because the one terminal can manage several sensors.
Okay, thank you. The next one, I'm not sure if I understand it right. Is there any incidence in results about position of the sound? Vertical, horizontal, 45 inclination?
In principle, not. Let's call it that way. In principle, the spectrometer probe can monitor in each orientation, but we have to take care for the conditions where the spectrolyzer or the eye scan are submerged. So if we use in the inlet typically a horizontal orientation, the reasons are at first or 45 degrees orientation. There are two reasons for it. At first, to avoid clogging, So if we would use a vertical orientation, the spectrometer or each other probe it's risky that it's clogged. And secondly, we have to take care that the measuring windows are not affected both by solids sedimenting as well as by air bubbles also from the automatic cleaning. So we have to make sure that air bubbles can leave the measuring gap. Typically, air bubbles go up, and therefore we do not orient the spectrolyzer and the ice can vertically, because otherwise the window would be horizontally, and then the bubbles would be on the upper window, and also there would be risk that solids will settle down on the lower window, and therefore in the submersed installation, in the influent and where solids are, and also in the final effluent where we use automatic cleaning via air, it's either horizontally installed or 45 degrees, but not because the measurement will be different, but the measurement might be affected by the water quality, by the conditions.
Okay, very interesting. Thank you. Next one. How do you clean when there is iron in the water, in the influent, and in the biological cleaning?
This is a very good question, because iron can be oxidized by the compressed air cleaning. Therefore, we use still the S-can compressor, but we manage the settings to be a very short jet of cleaning. So just 1 or 2 seconds of opening and solenoid valve, and the jet of air cleans the windows and it immediately closes down. So we use only the first pressure of the jet, but we avoid producing or generating too much oxygen besides the windows. So iron will be oxidized and will produce window fouling. So typically we use still the S-can compressor, but we reduce the duration of the cleaning down to a minimum.
Okay, thank you. And we're moving straight on to the next parameter. It's about COD. And the question asks, is the UV visible results exactly the same as per a lab method for COD measurement?
It won't be exactly the same, but it is well proven in many applications in municipal wastewater that it will be as accurate as needed, and it's often it's nearly always more precise than the laboratory results. So typically, if the customers take 2 or 3 lab samples and analyze it by lab, the deviation in between the lab results is bigger than the deviation from the spectrometer probe. As soon as S-can releases and global calibration and parameter that is calibrated for a specific application, like COD for wastewater, you can be sure that this is well proven in dozens of applications and will work in typical applications. So this is already verified by others. Other customers have proven this already. But
21
again,
years.
it's not exactly the same. Yeah.
21 years of custom experience. Yeah, I agree. In wastewater applications, are the best results in situ or by bypass installations?
If you ask me, I would say in situ applications, because by taking a sample out of the water and pumping it, you already start to change the composition of the sample. For instance, a pump will not will not collect all the solids that are present in the wastewater. In biological reactors, you can completely forget it to monitor in bypass applications. You have to submerge it, there is no question. In the final effluent, you can discuss it. The quality in the final effluent is rather stable, and it's low in solids, and you can find also good points to pump the water without changing the water composition. So in final effluent, bypass installations are also performing good, but in general, I would say submerged installations, if possible, should be done.
Okay, thank you. Let's move on to the next one. Are there any special requirements for the operation of ammolyzer in biological treatment? Thank you.
Are there any special? Sorry, I didn't get it.
Are there any special requirements for the operation of an ammolyzer in biological treatment?
Not really. It's a standard application for us. So we use optimized cleaning via compressed air to avoid drifting of the electrodes. What calibration has to be done properly in the biological treatment plant, but typically this is very easy because due to the changings in the water quality in the aeration tank, you can easily calibrate it, and I won't say there are any special requirements. I would even say that this is the most common application of the ammolyzer worldwide, the monitoring in the biological treatment. I would even say it's nearly designed for this application.
Beautiful answer, thank you. We're coming back to COD, I see. Next question, do you have examples from situation where COD load measured with cuvette method are less reliable than COD measured with an spectrolyzer?
Actually, I have to admit I don't know this, but we have for sure we have documents or scientific publications that prove that the spectrolyzer is monitoring the COD as accurate as the laboratory does it. So this we can provide, but more reliable, it's hard to find anybody that will confirm that an online instrument is more reliable than the laboratory.
I agree. I especially like the next question. Does the pre-calibration of the instruments work on different types of metrics in different wastewater treatment plants?
The four applications we presented here, the influent, the sewer system, the biological treatment, and the final effluent, we use different pre-calibrations for these different wastewater compositions. So the matrix of the final effluent is very different from the biological tank, and of course the matrix of the biological tank is very different from the composition in the influent, and therefore we use different pre-calibrations per these applications. So the COD or the nitrate as monitored in the final effluent is a different algorithm compared to the nitrate we use to monitor nitrate in the aeration tank, and the COD is a different algorithm than spectral algorithm than we use in the influent to monitor the COD. So these different matrices are already considered in our pre-calibration.
Thank you. And the next question is almost like a case study. A wastewater treatment plant wants to monitor BUD and CUD in influent, and also ammonia and turbidity if possible. Which spectrolyzer would be best suited for this application? Is a V3 too much for this? And in the effluent, they want to measure BUD, pH, and suspended solids.
In the influent, a spectrolyzer is not too much because the customer wants to monitor two organic parameters, CUD and BUD, and solids as well. And I would recommend to use here the spectrolyzer. In the final effluent and G series would do it as well. So and carbolyzer would work in the final effluent as well. And what was the other parameter? Ammonia, I guess.
Ammonia, yes. Ammonia.
Yeah, ammonia.
Let me check. There was one more. Ammonia and turbidity.
Yeah, turbidity was in the final effluent.
It's not said here. It just says they in influent BUD and CUD and ammonia and turbidity if possible.
In the influent, I wouldn't go for turbidity. I would go for total suspended solids in the influent. This is the better parameter to be monitored in wastewater influents. And in the final effluent, you can go for turbidity as well and use the eye scan to monitor turbidity and CUD, for instance.
Okay, thank you. So we're almost done with the questions, and we are actually also running out of time already. So I think we are almost done with all questions. Nonetheless, we will collect all of them and answer them in written form and put them on our customer portal. And everybody who has joined today will receive an email when they are uploaded, so you can then go there and have a look at all the questions. Yes, and now I would like just to remind you of our next webinars in case they're interesting for you. Drinking water takes place on the 11th of November, so in about 3 weeks, same time. And then in December, we have one more coming up, which will be about environmental monitoring on the 9th, on the December 9th, same time again. And as I mentioned in the beginning, this webinar has been recorded, so we will afterwards then take the video and put it on our website. So in case you have just seen parts of it, it doesn't really matter that much. You can have a look at it afterwards as well. Having said that, I really want to thank, first of all, Franz for showing us all the presentation, all different applications and so on. And of course, all and everybody of our participants for their time, for their interest, and of course for the great questions. Thank you so much and see you soon. Bye.